right. So we just finished up talking about momentum, which is essentially just the mass of an object times its velocity. Um, we talked about how that can be changed by an impulse. And we're going to continue thinking about that, but instead of just talking about the momentum of an object, we're going to talk about the energy that it has as well. So you can think about an object of having momentum and energy. All right. So we're going to first start talking about Emily du Châtelet, who was a French mathematician and physicist, was very bright. Actually, I don't know if she ever married Voltaire, but if you're familiar with uh, your literature from around the time of the Renaissance, uh, she was actually involved with Voltaire for many years. Um, but she actually settled a big debate. So in the 1700s, there was a big debate between physicists about whether the impetus or the thing um, that causes an object to move. Uh, some physicists, like in England, claimed that it was you could quantify the thing by calculating its momentum and saying like, oh, momentum describes everything about the energy or the impetus, the thing making this object move. Scientists in Germany said, no, it's actually mv squared. This has actually been a big argument going back and forth. And Emily du Châtelet actually published a scientific paper, and she cited just a simple experiment that's already sort of happened. And then through her proof and using this experiment, she pretty much demonstrated that it was actually the mv squared relationship. That's sort of the big overall uh, demonstrator of energy. So, just by the way, this is those of us that are like in academia and have PhDs and all that. This is usually how we communicate with everyone in our field. When we have an idea or we do an experiment, we'll publish a scientific paper. Um, and that's the way scientists have sort of communicated with each other for hundreds of years. So, if you're thinking about grad school or you're interested in a particular topic, you could actually go through Lenoir-Rund's library and start reading some of these academic, very high level papers in your field, and you can sort of get an idea of what's going on out there in any topic that you're interested in. But essentially, the paper that she wrote here basically cited this experiment where a brass ball was dropped onto clay. So just a little clay pad and a brass ball was dropped. And essentially, when this happens, it makes a little dent in the clay. But if you double the speed, so times 2 velocity, if you double the speed, the dent, I'll draw a bigger dent like this. If you double the speed, the dent actually quadruples in size. So a times 2 in speed would actually be a times 4 in size of the dent. So that suggests that it's not linear. It's not a 2-to-2 or 1-to-1 ratio, which is how she arrived at the mv squared actually being the way to describe something's energy. So that's going to come into play here. We're going to build up to energy and how that whole mv squared came about. But first, let's start with something a little more familiar. So we talked about impulse already when we were talking about momentum, and that's essentially just calculating how long a force interacts with something else. So you'll remember that this is the force times time. I also have it here. So that's how long a force acts on an object, but what we haven't talked about is sort of how far a force acts on an object. So you could have an object with a force acting on it, right? And that could be it could be across time, but we could also talk about a force acting on an object across a distance. Maybe this force pushes an object, I don't know, 10 meters to the right or some sort of distance. So what we're going to talk about is essentially if we replace the time of impulse with a distance instead, what does that do for us? Um, and essentially, this is the definition of work. So work is just the effort exerted on something that will change its energy. Okay, so we have effort exerted. We could certainly call that a force, right? And we want to, and the result of this work or this force will be a change in energy. So we'll say a change or a delta, final minus initial. The force applied is essentially going to add or remove energy from something. So there's two things that enter into the picture when work is done. Basically, there's the application of a force. Just talked about that. Okay, and then here, since we talked about this in the first bullet point, the movement of an object by that force, okay? So this is how we arrive at the idea of a force times a distance. So if we look at this picture, we can see this like sack of bricks or whatever being pulled up. We know that this is the starting point. So we could say this is our origin. We could also say the ground is our origin. We could label this as 0 meters, which means this guy here would be like -2 meters. This up here would be +2 meters. We could do the same thing with the ground. We could say the ground is actually 0 meters, and this guy is on the ground at 0 meters. Where the bag started is actually 2 meters. So we can actually put an origin anywhere we want to. And that's the thing with calculating work and energy, is it depends on where you put your origin. You can put it anywhere you want to, and all the math will work out, but you have to do everything relative to an origin when you're talking about energy. So I'm going to leave a note, all calculations are relative to an origin. All right. You can see some work is being done on this bag or this sack of bricks or whatever they're moving, because it starts here. We'll say that's its origin. Doesn't matter. And then it moves some distance d. Whoops. I'm getting ahead of myself. It moves some distance d. Now, the way it did that is it was pulled up by this force of tension. Okay, so there's my force due to tension. So we're essentially fighting gravity because we know that gravity does point down in this situation. You have that mg down. That's the weight of the bag. So this is our force pulling it up, is over a distance. So clearly there's some work being done here. So work generally falls into two categories, or there's at least two things going on. We have work done against another force, which is just like the example we saw, the tension pulling up, fighting gravity. So we had the tension going up, fighting gravity going down. There's also work done to change the speed of an object. Right, so there's some delta in our velocity. So in both cases, work is a transfer of energy. So anytime you're talking about work being done, work is not energy, work is the change in energy. And that's really important. So often the applied force in a work situation is not constant, but varies. So we're going to talk about the average force over a distance when we do this in calculations. So our calculations will be a little simplified. And we're just going to talk about the average force instead of trying to do a lot of tiny calculations while that force is changing. So you'll notice that we're multiplying, if we look at just units, we're multiplying a force, which is in newtons, by a distance, which is in meters. So a perfectly valid thing to call work, or the units on work, is actually a Newton meter, right? They're multiplied together, so it makes sense that they're a Newton meter. So that's a unit of work. You can also call it a joule. So 1 Newton acting over 1 meter would be 1 Newton meter of work, or 1 joule of work. All right, so now that we know how to calculate this, let's look at an example. So how much work is needed to lift a 200 Newton bag? Remember, that's weight. So how much work is needed to lift a 200 Newton bag of groceries to a height of 3 meters? Okay, and if we want to get fancy, we could also ask the question, how much is needed to lift it twice as high? All right, so for this first answer, this one's pretty straightforward. We know the force is 200 newtons, because it doesn't matter how hard we're going to pull up on this, right? All we need to do is just counteract the force due to gravity, or the weight of the object. Okay, so what we're doing is we're just going to take the groceries and its weight, and we're essentially moving that amount of weight. So that's going to be 200 newtons times the distance that we move it, 3. So that's going to give us 600 newton meters, or 600 joules. Now, the question is, if we double the distance, does it double the work? And for work, yes, that's totally true. That doesn't always work. But in this situation, if we want to move it twice as high, that'll be 6 meters instead of 3 meters. So essentially the calculation will be the same, and it turns out it's just going to double the amount of joules. Generally, work is only done by a force in the same direction as the distance traveled. This is something we won't deal with a lot in this class, but if you decide to take some more physics courses, this will come up more frequently. So if a force acts at an angle to the motion, then we have to think about the component parallel to the motion. All right, so remember when we used to, in previous modules, we'd break down, if we had some force, what we could do is we could grab its x component and its y component, and essentially take one vector and break it down into 2 that are perpendicular to each other, because this will always be a right angle. So that's all we're going to do here. We want the parallel piece. So if this force in particular is acting on this wagon, so in this situation, the parallel component of the force vector must be determined. So how do we find that? So the whole idea is we have our total force here. We know it's 50 newtons, but we want just the amount in this direction, right? We want that x component. Now we could, if we wanted to, we could also find out how much of this main vector is up in the y direction. But we don't care. We don't care what the work is doing in the y direction. We just want the x direction. That's all we care about, because the x direction of the force is in the same direction of motion, and that's what we want. Okay? So in just a second, we're going to talk about an example of how to do that. But for now, there's one more point I need to make. So if a force acts at a right angle, then no work is done at all. So if we had an object and it's being moved across some distance this way, we'll say, I don't know, a distance of 10 meters. And if the net force acting on it is like this way, what in the world is that force doing to actually help move this object to the right? All of the force is in the up, down, y direction. All of the motion is in the back and forth x direction. The force moving up and down does absolutely nothing to move this particle to the right or the left. So in this situation, you can see that this is a right angle. No work is done by this force. Right? I don't know what's pushing this particle to the right, but clearly it's not that force because that force is pointed straight up. So you can actually think about this. It's very interesting. If you think about a satellite orbiting Earth, so if this is Earth and you have a satellite in orbit, so the thing holding the satellite in orbit is weight or its gravity. Ooh, that should be an F. Let me try again. There we go. There we go. An F for force. The only thing holding this thing in orbit is like gravity holding it in its orbit, but its velocity and its direction of motion is always pointed forward while it's turning by the force. So there's actually no work done on this satellite because the only force acting on it isn't pointed in the direction it's going. The satellite's moving forward, but being pulled at a right angle at all times. So the distance is moving or the direction is moving, and the force pulling it, they're at a right angle. So no work's being done, even though this satellite is constantly moving. All right, let's look at this example again with some numbers and actually turn the crank here. So Preston places his daughter in a small wagon and pulls her 30 meters down the sidewalk. If he did so with a force of 50 newtons at an angle of 30 degrees, how much work was done? All right. Well, you'll remember from the last slide, we know that we're going to have to calculate this x component, this horizontal component of F, big F being 50 newtons. We want just this x component. All right. Well, first, what we can do is we can remember our trig functions because this is just a triangle. Okay, so we have our hypotenuse, we have our opposite side, and we have the side adjacent. And of course, that's adjacent to the angle that we're interested in. Okay, so we have this adjacent piece. So here we're looking for an adjacent piece. That's the thing we want, right? We don't know what it is, but we know we want it. So that is our f of x value. Okay, and we know the hypotenuse. The hypotenuse is the total big vector. Okay, so here's the hypotenuse. We know the hypotenuse is 50 newtons because looking at our original picture, right there is our 50 Newton vector. So now we just have to solve for this f of x, or f sub x. Okay, well, let's isolate this and do some algebra. Well, we have this 50 newtons in the denominator, so we can multiply it over. We can think of it as multiplying both sides by 50 newtons, right? Because then it'll cancel out on the right side, but then you'll have 50 newtons left over on the left side. So essentially, We're moving that 50 newtons over with algebra, and we've isolated f of x. So f of x is just 50 newtons times cosine of 30 degrees. You can do that in your calculator. Make sure you're in degree mode. Even if you use like Google to type in your calculations, you got to tell Google to do it in degrees. But essentially, this is going to give us 43.3 newtons. Okay, now we have the work, or sorry, we have the force, which we can just plug in here. Okay, we're not plugging in the 50 newtons, we are plugging in just the x component. Okay, and we're going to multiply that by the distance being pulled, so 30 meters. And that's going to give us, in our rounded, that's why I have the squiggly equals, that means it's roughly equal to. So this is approximately 1,300 joules of work being done on this kid in the cart. All right, so we've talked about work, which is how far a force acts on an object. Well, let's talk about how long it takes for the work to do this. This is going to be different than impulse. Okay, impulse is just how long a force. Let's do this. Impulse. Impulse is how long a force acts, F times T. Now let's talk about the definition of work when it comes to how long it takes to do the work. So to talk about that, we need to understand the concept of power, which this is essentially just a measure of how quickly work is done. So power is just the amount of work done per time it takes to do it. So essentially, how much work you've done. So how much work when Preston was doing work in the previous example, how long did it take him to do that? So it's the work done divided by how long it took you to do that. So if Preston did all that pulling in 15 seconds, we'd take his work, which was 1,300 joules, and we could divide it by whatever time it was. It could be 10 seconds, it could be 20 seconds, just depending on how long it took him to go that 30 meters. But the unit of power is a joule per second, and you can see that here just from writing that out. And it makes sense because we have a work in the numerator, joules, divided by time, which would be seconds. And we can reduce this, instead of saying joules per second, this is actually a watt. And this should sound familiar because you can talk about light bulbs and the amount of power they give off, 40 watts, 60 watts. Engines sometimes are measured by their output in watts. In the United States, though, we customarily rate engines in units of horsepower. All right, so this is power. And then, of course, electricity, we talk about in kilowatts. So you remember that 1 kilowatt is just 1,000 watts. So if I was talking about 3 kilowatts of energy, that'd be 3,000 watts. One useful tidbit here, 1 horsepower equals 746 watts. Something to note, though, looking at these next 2 bullet points, so a high power engine does work rapidly, makes sense. So a car engine that delivers twice the power of another doesn't actually necessarily produce twice as much work. So twice the power could be twice as much work, but there's other ways to get there. So let's think about this. If we're wanting twice the power, we have 2 ways to do it. We can do twice the amount of work in the same amount of time, or we can do the same amount of work in half the time. right? So if you think about it, if you and your sibling fold the same amount of laundry, but your sibling is twice as fast, even though the number of shirts you're folding are the same, your sibling's exerting twice the power. Now, if you can fold double the amount of shirts that your sibling can in the same amount of time, then you're exhibiting twice the power. So you can do things shorter to increase power, or you can do more stuff in the same amount of time to increase power. So let's think about this example here. So how much power is expended in lifting a 4,000 Newton piano a vertical distance of 4 meters in 2 seconds? Okay, so you can see the piano over here. We'll say that maybe this is really close to the ground. You can't tell in the picture, but we'll call this the origin. And we'll say that this is our, not 14 meters, no. This is our 4-meter distance, which is about 12 feet, a little more than that, maybe 13, 14 feet. Okay, so if we're going to lift this piano a vertical distance in 2 seconds, so our interval is 2 seconds, how much power is, how much power is needed to do that? And then if we do it in 1 second, so we're really yanking it upward, how much power would be required to do that? So in the first situation, remember, we're just going to do the work divided by time. Well, work is just force times distance. So the force we're overcoming, it doesn't matter how hard we yank it up. We're just wanting to overcome that weight. So it's going to be 4,000 newtons up times the 4-meter distance. And then we're going to divide that by 2 seconds. It's going to give us about 8,000 newtons. If we did it in half the time, you'll notice that I reduced my time to 1 second. Well, that's going to essentially, like I talked about on the previous slide, it's going to double our power requirement. All right, so we've hit work, we've hit energy. Nope, we've hit work, we've hit power. Now we're going to talk about energy. So energy is just essentially something that enables an object to do work. Okay, so if an object can do work, can do F times D, then that means it has some sort of energy. And energy is also measured in joules. So energy appears in all sorts of forms, but the two we're going to talk about right now are just potential and kinetic. And these two are types of mechanical energy. Right, so things are moving, they have to be in a specific position. There's actually a physical, like, everyday change that you're seeing, and that's the idea of mechanical energy. So let's talk about the potential energy of this mechanical energy first. So the energy stored in readiness is called potential energy. This is essentially a stored energy, and it's ready to be released to do work. Okay, it's not doing any work yet, but there's something there that could allow it to. So examples include a stretched or compressed spring, a drawn bow, as you can see over here. The string in this bow is pulled back, so it's got tension in it. So I can actually, oh, that doesn't show up on her shirt. Okay, I'll write it up here. It's got a tension vector. There's a force in there. It's just not released yet. There's also like a stretch rubber band, which works very similar to a spring. We could also have potential energy stored in fuels. So the unburned fuel in your gas tank is also a form of potential energy. Even that has to do with sort of the location and mechanical stuff. It's mechanical at a molecular level, that energy stored in the molecules. But you can also think about like pulling a rubber band. So if the rubber band is normally this size and then you stretch it, right? You've changed you went from some like a relaxed distance D1, you've went to some new stretch distance D2. So that's why I say potential energy is the energy of position. Just like in the fuel, those molecules, they're structured in a certain way, so that's where you're going to get that energy. So potential energy depends on where something is and how you've defined its position, just like we did with the stretched rubber band. So work, as we know now, is required to elevate objects against Earth's gravity, because we've talked about mg pointing down while you're trying to act against it. So the potential energy due to the elevation gained by an object is actually gravitational potential energy. So whenever work is done, energy is exchanged. So what this means is essentially an object can have energy, it can have gravitational potential energy, but like we talked about earlier, if work is being done, it's changing the energy that the object has. So the amount of gravitational potential energy possessed by an elevated object is equal to the work done against gravity to lift it. So that's why we've been using the when we put in a force, when we lift something, that's why we've been using the weight of the object, right? Because we're doing work against gravity. All right. So to lift an object, its weight must overcome mg, right? Because that's the force down. Additionally, it must move from the ground to some height. So the distance, so normally when we talk about force times distance is side to side, but we're just going to call it a height h. So essentially the work done to lift an object and to calculate its gravitational potential energy, remember they're equal. Work done to move an object up is going to be equal to its GPE. Well, we know that work is just force times distance. And we now know why we're using mg as the force. And well, the distance, we're just moving up h. Distance, it's just the height. This is actually how you calculate the gravitational potential energy. Is just GPE. A lot of times you'll see this as just PE for potential energy. You can put the G in front of it if you want to, but to calculate gravitational potential energy, it's just mgh. So remember that h is the distance above some chosen reference level. And then the gravitational potential energy will always, in the situation, always be relative to that level. Okay, so that's important. Over here in this example, you can see that this bag of bricks again, it starts from here. We could call this our origin of no change, 0 meters. And then we could calculate the gravitational potential energy. That's totally fine. We could, oh, let me do this in a different color if I can erase. Yeah. We could call the floor our origin. If that's the case, if we start with the ground or the floor, that means there's already some initial potential energy here. Right? It already started above the floor, and then it's going to move even further. So we already start with a head start. We start with some initial GPE and then move to a final. So we start with some, we get even more if we're using the floor as our reference. But if we use the starting point here, and that's our origin, and we move through H, I don't know, maybe it moves 2 meters or something. we actually, when we do this, the math is going to work out. So we go from 0 to, I don't know, let's say this is a 1 Newton bag or something. You can see that we move over this distance of 2, right? And we've got some weight, we don't care what it is, times 2 meters, right? That's our GPE, our gravitational potential energy, from this origin where the bag starts. But if we wanted to do it the quote unquote green way, maybe it starts already with mg 2 meters, but then moves up here. So it went to mg 4 meters. The difference is what matters, okay? So no matter which way we do it, even though it started in the green one, it started at 2 meters above the ground, it still only traveled 2 meters. So we're talking about the change here. Same thing over here. Even if we say it started at 0 meters at our orange origin, it still only traveled 2 meters. So the distance, no matter where we put our origin, is the same. And we're not talking about like initial and final energy separate. We're actually just talking about the change. So even though it started in one situation with some GPE and one situation without, doesn't matter because we're just talking about how much the change is, not what they start with, if that makes any sense. So the whole point of this is no matter where you put your origin, your math is going to work out if you just leave your origin there. You'll still get the same GPE. So ultimately, same gravitational potential energy for both. So let's look at this example here. So we have how much work is done in lifting this 100 Newton block of ice, a vertical distance of 2 meters, okay? So the whole point here is we've got this distance of 2 meters, okay? And then if we do the same amount of work by pushing it up this ramp, how does that change our gravitational potential energy, or how much does that change the work going into this? And essentially, if we look at the straight up example, we have MGH. Well, we know that it's 100 newtons that we're trying to work against here times the 2 meters straight up, just lifting it to the top of the ramp. And that calculation gives us 200 joules. But if we think about it in terms of pushing up the ramp, notice what happens. So we push this up a 4-meter ramp here. So we've doubled the distance that it travels. All right, so D is actually going to be 4 meters. But we're also thinking about the vertical direction, which means we need the vertical component of the force, right? We're not pushing side to side to talk about work. We want gravitational potential energy, which is up and down. So I won't do it here, but you can use the sine function to get the length of Fy. So this is essentially just the big vector times sine theta, just using trig, and that's going to give us 1/2 in there from the sine of 30 degrees. Whoops. And essentially what's going to happen is when you multiply all this out, you get the same answer again. All right, you still get 200 joules, but you got to remember that the distance up the ramp was actually doubled, but because of the angle, it actually cut the amount of force needed in half. So in both cases, the block has the same potential energy of 200 joules, the same amount of work is done. The ramp just makes it easier. You have to go over a longer distance, so it takes longer to add up to 200 joules. But essentially, the main thing that matters is the height here. The height's the same at the end of both of these problems. Therefore, the GPE will be the same. so yeah, basically right before we jump to kinetic energy, the potential energy of this ball here, this 10 Newton ball, is the same no matter what. Whether you set it straight up here, whether you push it up a ramp, and you can do the math yourself if you'd like, or if you do like 3 1-meter increments, it doesn't matter. All of these 30 joules every time. So the path taken doesn't matter. Path doesn't matter at all when you're talking about gravitational potential energy. All right. Okay. Just looks like one more example and then a summary slide. So yes. So let's talk about kinetic energy now. So if an object is moving, it can do work and it has energy of motion, right? So that's going to be kinetic energy. That's the other type of mechanical energy we were talking about. So the kinetic energy of an object depends on the mass of the object as well as its speed. So it's sort of like momentum, right? So we know that kinetic energy depends on mass and speed, and we know that momentum does as well. But remember what Emily du Châtelet said? She confirmed that it was the energy, not the momentum, but the energy of an object is proportional to mv squared. Well, it turns out all that's missing is a 1/2 in front of that. Okay, so we can actually calculate kinetic energy with this simple 1/2 mv squared relationship. And this is essentially just how much energy an object has as it's whizzing through the air. Or your car traveling down the street, because it has a mass, it has a velocity, therefore it has energy. So the kinetic energy of a moving object is equal to the work required to bring it up to speed from rest. Yes, okay, so the kinetic energy of a moving object is basically if you go from 0 meters per second to some velocity, I don't know, 10 meters per second later, this change here, this change in your velocity, well, the kinetic energy that you get is from the amount of work it takes to do that. So how much work did it take to do that? Don't know, but whatever amount of work that was needed, that's the amount of kinetic energy you're going to have. So essentially the work done to get you from rest up to speed, maybe, I don't know, it was 1,000 joules, then you're going to have 1,000 joules of kinetic energy. Okay, one example here. So if we have a 1 kilogram ball, so here's our mass, is traveling at 10 meters per second velocity, what is its kinetic energy? Okay, so that's a simple calculation. We already know that Ke equals 1/2 mv squared. What happens to the energy if the velocity is doubled? Now, this is where it gets a little weird because you'll notice velocity squared. So if we double it, if we double velocity, we're not going to just double kinetic energy. Something weird is going to happen. So for the first part, that's just a simple calculation. So that's just plug and chug, right? The 1 kilogram ball mass times the velocity, which is 10 meters per second. So this 1 kilogram ball has 50 newtons. I'm sorry, this should be 50 joules of energy. And then if we double the velocity, look at what happens. Right? If we double the velocity, you might say, oh, we double the kinetic energy to 100. No, we quadruple the energy. So the magic happens here. When you double something and then square it, right? It's not just a regular doubling anymore. So that's the whole point here is that changes in velocity of an object really change your kinetic energy. Instead of just like a doubling of velocity would, double your momentum, a doubling of velocity actually quadruples your kinetic energy. And then, of course, we're going to talk about this more in the next lecture, but I want to bring it up really quick. The whole idea of conservation of energy essentially just says energy can't be created or destroyed. It can only be transformed from one form to another. So the whole idea is essentially just potential energy can be transformed to kinetic energy and vice versa. So you can see we have some origin here with this pendulum. This is our potential energy. Well, as it moves, it loses potential energy, but it's moving, right? So it's got to have some kinetic energy. When it gets down here to the bottom of its swing, there's no height left to drop, right? It's already dropped as far as it can. So there's no potential energy. And then as it swings back up to the other side, now it's all potential energy and it's got to stop to turn around, right? So for a brief moment, when it stops, well, velocity is zero, which means there's no kinetic energy. Just for a minute, and then it swings back through and changes energy again. So just a quick summary. I'm trying to finish up here at the last little bit, so this isn't too long. But we did talk about work, which is just the force applied over a distance. We talked about power, which is how long it took to apply that force over a distance. We talked about potential energy, which is energy of position. So you can bring something up to a bigger height, give it more potential energy. And then you can have kinetic energy, which is essentially just energy in motion, which is dependent on your velocity squared. So next time, we'll talk about more of this whole idea of conservation of energy and how we can turn energy, like kinetic energy, into potential energy and vice versa.